Before we go into how drying works, we need to differentiate between dewatering and drying. What we mean with drying is the process by which water is evaporated from the drying goods, typically by using air or overheated steam. Mechanical dewatering is a process where you remove water in another way. Since the evaporation enthalpy of water is high, we can save a lot of energy if we design and use a good dewatering step before we dry our drying goods. Thus, when we wash clothes in a washing machine, for example, the washing machine uses mechanical dewatering before ending the program, before we dry our clothes. First, it simply lets gravity do its work and let the water pour out from the clothes, in essence a filtration step, and then it centrifuges our clothes. Apart from filtration and centrifugation, pressing is a common mechanical dewatering process. Many of you probably use that process daily at your home, for example, clenching your hand through around the dishcloth or similar, after using it to clean some surface. The mechanical dewatering steps typically use much less energy per kilogram of removed water than the evaporation enthalpy, and thus mechanical dewatering typically saves energy, saves money, and lowers the environmental impact of the process. There is, of course, a limit on how much water that can be removed by mechanical dewatering. A dewatering process that is not mechanical is evaporation. If you have solids, for example salts, dispersed or dissolved in water, the water content needs to be reduced a lot before drying. A downside with evaporation is that the energy needed per kilogram of water removed is essentially the evaporation enthalpy of water. However, in a multi-effect evaporator, the steam produced in one evaporator can be used to dry another, and so on, thus reducing the energy need considerably. After the dewatering, we can start to dry our goods. In the beginning, we might have drying goods that have a fully wetted surface. Under such conditions, drying is analogous to evaporation from a liquid surface. As the liquid surface is essentially constant in the beginning, so is the drying rate. However, as soon as the surface partly dries up, the drying rate decreases, and when the surface is entirely dry, the drying rate is determined by slow diffusion in the pores inside the material. The drying rate continues to decrease since the distance the water needs to travel to get to the surface of the material increases as the water content decreases. So if you, for example, dry tea leaves or herbs, you can increase the drying rate by gentle stirring, such that the wetter material comes in a better contact with the air. If you dry jeans or clothes made of thick fabric in a drying cabinet, turning the clothes inside out increases the drying rate. Increasing the drying rate in this way decreases the energy demand. The energy demand of the drying process is high, since the water needs to be evaporated and since evaporation enthalpy of water is high. This is a reason why we in the separation process course focus on drying rather than dewatering, to try to make sure that you understand how drying works and why it uses so much energy.